Welcome to the course on plasma physics and applications. Today we will continue our discussion on thermonuclear fusion by taking a very simple approach to design the main elements of a magnetic fusion reactor. We have seen together what the main elements are for the reactor, but we are now ready to really define the key design parameters. The design parameters result from constraints that are coming from engineering, but also from nuclear physics. And this will be combined with the need to minimize the cost of electricity to lead to a generic and very simple design of a reactor. I'd like to start the discussion by reminding ourselves what the schematic is of a fusion reactor, at least as we anticipated today. In general, we have fuels that are coming from outside in the form of deuterium and lithium. They'll be injected into the system. The deuterium will be going into the plasma, which will form the core of the reactor. The lithium will be part of what we call the blanket. I remind you that the blanket has two main jobs. First, it has to get the heat from the neutrons issued by the fusion reactions. The heat will be collected in a heat exchanger and therefore will be used to generate electricity by a steam generator. And second, the blanket needs to be producing tritium. Tritium will be produced by the reactions between the neutrons issued by the DT fusion reactions themselves and the lithium that will be present in the blanket. So the tritium, once more, will be only present in a closed loop within the reactor. It will not come in from outside, nor will go out from the reactor. So this is a generic scheme with the plasma forming the hot core, of course, of the whole system. But as we said in previous lectures, we will concentrate in this course mostly on the magnetic fusion approach, and that is the approach in which we confine the plasma using magnetic field. So we need to consider that around the plasma, not only there will be a blanket, but it will also be a magnet, as illustrated in this 3D view of a fusion reactor, a magnet that will produce the field with which we will confine the plasma. We have said in the previous lecture that the first reactors will operate between what we call break-even and what we call ignition. I remind you that break-even is a situation in which the fusion power produced by the plasma is exactly equal to the input power. So the capital Q, which is the fusion gain, is equal to 1. Ignition is a situation in which there is no input power from outside at all, and so all the heating from the plasma comes from the alpha particles produced by the fusion reactions themselves. So that corresponds to a fusion gain of infinity. In terms of the confinement quality, we can quantify that as the product of the density of the plasma and the confinement time for the energy, n times tau E. And for the two situations, we have about 1 10 to the 20 per cubic meter times seconds for break-even, and 6 times that is 6 times 10 to the 20 per cubic meter times seconds for ignition. So we'll be in between these two values. Of course, together with the value n tau E, we need to have a temperature that's large enough for the fusion reactions to take place, typically 10-15 keV. What are the design goals we are considering for this exercise? What we like to do is to minimize the cost of the reactor, because that will correspond to minimizing the cost of electricity. We also like to minimize the requirements that the design imposes on the plasma performance. We know it's difficult to confine the energy and the particles in the plasma for a long time, so we don't want to make it more difficult by imposing too large values for tau E, the confinement time for the energy. It's also difficult to hold the plasma stable if the plasma has a very large pressure. That is, the beta of the plasma, which is the ratio between the plasma pressure and the magnetic field pressure, has to be as small as we can from the engineering point of view, in order not to make it too difficult for plasma physics. So these are the goals. What we need to optimize are the size and the geometry of the reactor and the value of the intensity of the magnetic field that will provide the confinement. In a somewhat more sophisticated part of the exercise, one can also optimize the combination of density, temperature, and confinement time for the plasma core. And what we need to consider in this optimization exercise are the constraints coming from physics and engineering. So we start by looking at the simplified geometry for our magnetic fusion reactor. We consider a toroidal shape, for example, that of a tokamak. Toroidal shape characterized by a major radius, that's the radius of the torus. We have the size of the plasma here, indicated by A. So let's draw the plasma in red. We have the size of the blanket and the shield that will surround the plasma, indicated by B, and here in green. And we have the thickness of the magnetic field coils, or magnet, that I represent here in purple, C. I noticed that I used a circular cross-section from the plasma and the magnets just to keep it simple. The other parameters that I need to consider are, of course, the fusion power, or the electrical power that we require for the reactor, the intensity of the magnetic field, and the plasma parameters that would be typically the confinement time, density, temperature, and the value of beta. What are the constraints? Let's look at them one by one. First, from the engineering point of view, we can call that a constraint. It's sort of a requirement for the power plant to produce a certain amount of energy or power. We may require something like a gigawatt of electrical power, for example. Second constraint is the wall loading, as we call it, LW. That's the amount of power we can cope with the materials that face the plasma. Typically, that cannot exceed something like 4 or 5 megawatt per square meters. And that power comes from the plasma losses and the neutrons. We want the magnets to be superconducting in order for the recirculating power in the plant not to be too large, and in order, of course, to have an optimal production of energy from our plant. In order for the magnets to be superconducting and to remain superconducting, they must be below a certain curve in the J, B, and T space. J is the current density, B is the magnetic field intensity, and T is the temperature in this case. So in practice, for the materials that we like to use, at least in the first generations of reactors, that means that at the coil position, the maximum field cannot exceed something like about 13 Tesla. We also have constraints from physics and or nuclear physics in particular. We have the value of the fusion rate determined by the fusion cross-section. For example, at the value of temperature that we're interested in, such as 15 keV, that's a value given by nature. And also we have the various processes that have to happen in the blanket and in the shield, which are represented by cross-sections as well. The processes are the neutron multiplication. We need to multiply neutrons before we breed the tritium by reacting with lithium. We need to multiply them because, of course, we can't just rely on a one-to-one correspondence between the number of fusion reactions and the number of tritons we produce, because there may be losses of neutrons. There will be losses of neutrons. We need to slow them down. And the reason for that is that we have to breed tritium by having the neutrons reacting with lithium, and the cross-section for such reaction is much, much larger at low energies. The plot on the right illustrates that. If I take the cross-section here that I'm highlighting with my blue pen in blue, this is a cross-section from breeding tritium by reacting with lithium-6. You can notice that as I go down in energy, this cross-section increases very significantly. In fact, I can keep going down in energy and the cross-section will become much, much larger. So I need to slow down the neutrons in order to have an optimal breeding of the tritium. The other thing I notice in this plot, I like to remind you of that, is that if I consider the breeding reaction with lithium-7, which is this cross-section, the value of the cross-section is much, much lower than for lithium-6. So we'll only consider lithium-6, and we, in fact, probably don't even need to enrich lithium in the actual production of the blanket because of such a huge difference between the two cross sections. So once we have slowed down the neutrons, of course we need to do the breeding, but we don't have to forget that we need to shield the superconducting coils, and in fact the rest of the plant and the rest of the environment, from the neutrons issued by the nuclear reactions. So these are the 4 jobs that the blanket and shield elements need to perform. Let's look at them one by one, and also in a quantitative way, to evaluate the thickness that we need for each process. Here again I put the schematic view of the blanket and shield. The different layers that do the different tasks are indicated, but I'd like to underline that in practice, of course, in an engineering design for actual reactors, the different layers will be combined. So the thickness that's needed for each process, as in fact in all collisional processes, can be evaluated by 1 over the number density of the targets that provide that process times the cross section that represents the probability of occurrence of that process. First process we need to evaluate is a neutron multiplication. We can take the example of beryllium. Beryllium is a neutron multiplier that's used in a variety of applications. So the thickness that we need for this process is given by 1 over the density of beryllium times the cross section that represents this process. So if we take the values for the density and the cross section, we come out with a relatively small thickness of about 13 centimeters. As we said before, we need to slow down the neutrons in order for the breeding to be more efficient. So we can use lithium itself, not only for breeding tritium, but also for slowing down neutrons. So we can evaluate the length over which the slowing down process will take place as 1 over the density of the lithium times the slowing down cross section, which is about 1 bar or 10 to the minus 28 square meters. So that is corresponding to about 20 centimeters, a value that's not insignificant, but again not unrealistically mountable in a blanket in a practical reactor. Third process is the breeding of tritium, finally, with slowed down neutrons. So suppose we are able to go down to room temperature, which is about 1/40th of NeV. And here I consider lithium in its natural composition, so I don't enrich the lithium blanket with lithium-6. So lithium-6 is only 7.5%. So the thickness is calculated in the usual way, 1 over the density of lithium-6 times the breeding cross-section. And for the density of lithium-6, I take the density of lithium times 6 itself, as if it was pure, times the isotopic fraction, so that's 7.5%. But as said a couple of times already, but now underlined by the quantitative factors here, the cross-section for the breeding is so large at these room temperatures that even 7.5% of lithium-6 doesn't add a significant thickness to my blanket for the tritium breeding to take place. So that's only about 0.2 centimeters. So the key here is that the breeding is actually relatively easy as long as we have slowed down the neutrons significantly. Finally, we need to shield the coils and the rest of the plant from the neutrons, and that in fact is the task that imposes the largest of the thicknesses. For example, let's say we want to reduce the flux by a factor of 100, so we only allow 1% of the neutrons issued by fusion reactions to arrive to the coil surfaces. So the intensity of the neutron flux is represented by I here. It's going down exponentially with the distance, and the characteristic length in the exponent is a combination of different processes, but we can assume is dominated by the slowing down process, as we have seen before. So if we take that length, we impose that the intensity goes down by a factor of 100, we get the shielding thickness, which is the log or natural log of 100 times the slowing down thickness we calculated before. That's about 1 meter. So really that's the dominant part of the thickness that we have found in this evaluation of the need for the blanket and the shield to do all the 4 tasks that they are required to do in a reactor. The total thickness is therefore B, equal to the thickness required for multiplying neutrons, only a few centimeters. The thickness required to slow down neutrons, that's significant, it's about 20 centimeters. The thickness needed to breed tritium with the slowed down neutrons, and that's almost negligible, it's a fraction of a centimeter. And the thickness needed to shield the coils from the neutron flux, and that in fact is the dominant factor. So we get about 1.35 meters of thickness for the blanket and shield. However, considering again that the different layers are combined and that this exercise aims at providing only a rough estimate, we can assume a slightly lower value, say of about 1.2 meters. We can now move to the minimization of the cost of electricity. And we notice that the cost of electricity in a fusion power plant will be proportional to the capital cost for the reactor. That's similar to the situation of fission plants, in fact, where the operational cost and the cost of the fuels are much lower than the capital investment in building the reactor. So when we want to minimize the cost of electricity, we can minimize the reactor cost. Of course, we have to minimize the reactor cost per unit power. But in a complex system, that is actually corresponding to minimizing the volume of the complex systems divided by the unit power. So let's evaluate that. The volume of the complex system per power is given by the volume of everything in my reactor except the plasma. Because the plasma is essentially only very few particles that we put in a vacuum and they will be ionized. So it is not something we build with high technology. So I need to evaluate the volume of the system overall minus the volume of the plasma. So that's 2 pi r0, which is the circumference of the torus, times pi times a plus b plus c square minus a square. And of course we need to divide that by the electrical power produced by the reactor. And the electrical power is equal to 1/4 times the efficiency with which we transform fusion power into electricity times the energy produced in each reaction. So that's the energy of the alphas, the energy of the neutrons, and the energy produced in the tritium breeding reaction in a blanket with lithium-6 times n squared, the density squared, the fusion reaction rate, and of course the plasma volume. Now we use the constraint on the wall loading to get the value of the major radius R0. And the way to use that is to take the maximum wall loading we can accept times the area of the plasma, and that should be equal to the power in the plasma. Here I only take the neutron power because I consider that as the only unavoidable part of the power that will go onto the wall. And of course it's an assumption to simplify the calculations. Now we know that the neutron power is equal to the fusion power, which is the electrical power produced by the plant divided by the efficiency with which the fusion power is transformed into electricity, times the fraction of the energy in each reaction that's associated with the neutrons. So En divided by E alpha plus En plus E lithium. So let's go on with the evaluation of the product of the maximum wall loading times the surface. Again, the maximum wall loading times 2 pi a 2 pi r0, which is the surface of the plasma, is equal to the neutron power. So we can extract r0. So r0 is p over eta t times the fraction of the energy that's in the neutrons divided by 4 pi square times the radius of the plasma times the maximum wall loading we can cope with. Now these are numbers that we know, and we can assume a value for the thermal efficiency eta t. Let's say we take 40% for eta t. So we get to value for R naught, the major radius of the plasma, which is about 0.04 times the electrical power of the plant divided by the radius of the plasma and the maximum wall loading we can tolerate. We can now insert the value of R0 we have just found in the ratio we need to minimize, that is the ratio between the volume and the power. So this ratio is now 2 pi squared divided by the power times the geometrical factor times R0 expressed as 0.04 PE over A LW max. If I just put the constants together, I get 0.8 times A plus B plus C squared minus A squared divided by A times the wall loading. And I notice that the electrical power, PE, has been simplified. This is the quantity to minimize, and I notice that a key parameter in the whole exercise is and will be the maximum wall loading. So it's a very simple minimization, of course, in terms of the maximum wall loading. The more wall loading we tolerate, the better we will be off with the reactor design, in the sense that we will be automatically minimizing the volume of the complex system, that is their cost per unit power. Now we are ready to continue with the determination of the parameters of the reactor, because B we know, B is determined already from the blanket physics. We need to find now A and C. That is the size of the plasma and the size of the magnet. In terms of the thickness of the magnet, here I remind you what we're talking about in a more realistic situation than our schematic drawing. This in fact is the magnet designed for ether. So the thickness is really the term C here. We would like that to be minimum, but we would like to be compatible with the maximum allowed stress on the structure of the magnet itself, stress that comes from the J cross B force. In the magnet, of course, there will be current that will flow, and this current will produce a magnetic field with which it will interact to produce a J cross B force. This is the force that's responsible for the stress. If we do a simple calculation, which we don't report here, using only the tensile part of the stress, we obtain a value of C, indicated here, related to a parameter alpha, and related to A and B, so related to the other two geometrical parameters we discussed already. The parameter alpha contains essentially the intensity of the field at the coil squared divided by the maximum stress that we can tolerate for the integrity of the coil itself. Now we can actually choose the intensity of the field at the coil, just observing that it is difficult for the plasma to reach high beta. So if we don't want to make it too difficult for the plasma side, we need to take the maximum field we can have at the coil. So the pressure for the plasma, we have it would be easier to have that high enough without violating stability limits, for example, because that would correspond to large values of beta. So we take the maximum field of the coil that we can have in order for the coil to remain superconducting. As we said before, that's about 13 Tesla, at least in the magnets that we can consider today. So we take a maximum value for B coil. We know that typically the maximum stress we can tolerate is of the order of 300 megapascal, so we insert that into the expression for alpha, and we get a value of alpha that's about 0.1. So with that we calculate C, and that gives C equal to 0.22 times A plus B. So we have determined B from blanket physics. We have expressed C in terms of A and B from considerations on the magnet. Now we go back to our minimization of the cost of electricity to evaluate A. We write again the quantity we want to minimize, that's the volume of the complex system divided by the power. So we have written exactly what we have found before, except that instead of C, we have put what we had just derived for the magnet thickness, that is 0.22 times A plus B. And by putting numbers and developing the square, we get approximately 0.4 divided by A times the maximum overloading times A squared plus 6AB plus 3B squared. Just divide by A, and we obtain a very simple expression in terms of A and B. We define a function of A as A plus 6B plus 3B squared over A, that is the parenthesis we have here, because that is the function we need to minimize. So the minimum of f of A is what we want. That's a trivial calculation, so it's 1 minus 3B squared over A squared, that has to be equal to 0, which gives that A has to be equal to the square root of 3 times B. So this minimization tells us what the value of A should be in terms of the value of B. C, we had already, it's 0.22 times A plus B. So that's 0.22 times the square root of 3 plus 1 times B, which is about 0.6B. So we have everything now. And we can put the numbers. B is equal to about 1.2 meters. Blanket thickness. A is about 2 meters, a little more, 2.1 meters. That's the radius of the plasma. C, the thickness of the magnet is about 0.7 meters. We are now ready to put down numbers for the resulting reactor geometry and even the plasma parameters, the main plasma parameters. The major radius, R0, 0.04 times the electrical power that we want divided by the plasma radius that we now know, and also divided by the maximum overloading. Let's take two numbers for these two parameters. Let's take a gigawatt for the electrical power, as we said at the beginning, and let's take a 4.5 megawatt per square meter for the maximum overloading. So that will allow us to calculate the value of the major radius of our plant, of our tokamak. So we have a gigawatt on the top, 4.5 megawatt per square meter at the bottom, 2.1 meters, which is the value of A we found before, and the result is a slightly more than 4 meters. We can therefore evaluate the plasma surface. That's 4 pi square R0A, and that's about 350 square meters. It's interesting also to evaluate the plasma volume. It's 2 pi R0 times pi A squared. That's about 365 cubic meter. So what's the power density in such plasma? That's the power in the alphas plus the power in the neutrons divided by the volume. If I put in the numbers, I obtain something like 6 megawatts per cubic meter. The next parameter I'd like to calculate, it's a key parameter for plasma physics, that is beta. But for that we need the plasma, we need the value of the magnetic field in the plasma, which I call B0. That's B at the center of the plasma, which is a value of the radial position equal to the major radius. How do I calculate that? I know that the field scales at 1 over r, and I also know that the field at the coil has its maximum value that we took of about 13 Tesla. So we can just evaluate B0 as B max times the radius which I have my coil divided by the radius of the torus. That's about 2.7 Tesla. If I just represent what we've done graphically, we know the field scales as 1 over r. We know the field and the coil. The radius of the coil, position of the coil is r0 minus a plus b. And we calculated the value of the field, which we call B0, at R0. If I go on the layout of the tokamak, that implies knowing the field here at the coil, and going down as 1 over R, and finding B0, where the center of the plasma is. So with this value of 2.7 Tesla, we can evaluate beta by assuming a confinement time of about 2 seconds, density of about 10 to the 20 per cubic meter, and a temperature of about 15 keV. Beta is equal to NT divided by B naught squared divided by 2 mu naught. And if I put the numbers, I get a value of about 8%. In summary, we have seen together that a minimization of the cost of the reactor, together with constraints that come from nuclear physics and engineering, can lead, even in a very simple approach, to a general definition of magnetic fusion reactor design that is capable of producing about a gigawatt of electrical power. We noticed together that one of the key parameters, perhaps the most important parameters, is the wall loading we can tolerate. That is the maximum amount of power per square meter that the surfaces that see the plasma first can tolerate without being destroyed. We have defined together the reactor geometry and even the plasma parameters, or the main plasma parameter that the reactor needs to have. We noticed that the size of the reactor cannot be that small, so we can't really have a tabletop reactor if we want the reactor to be self-sufficient in terms of the production of tritium. And that size is dictated by the size of the blanket. We found something like 1.2 meters. So for the challenges that this design poses to the plasma, we have summarized them in a few parameters. We need to have a fusion plasma of about 10 to the 20 per cubic meter of density that's produced. It has to be heated up to about 15 keV. It has to be confined for long enough, about a couple of seconds of confinement time for the energy. And it has to be maintained stable with a plasma beta, that is a ratio of the plasma pressure to the magnetic field pressure, of about 8%. These are the challenges that plasma physics need to face in order for this reactor to comply with the engineering and physics constraints and produce a significant amount of fusion power and electrical power.